हेलो चेक। एक सेकंड दोस्तों, आ रहा हूँ मैं। Yo people, what's up? The camera is a little टेढ़ा मेढ़ा, but don't worry, this is good enough. So I believe we are live. Welcome to Catalysis by Vedantu. My name is Pahul. If I'm audible and visible, please write yo in the chat box. You know what to do. 136 people. यार जब भी एक चैप्टर नया शुरू करो ना, yeah, whenever I start a new chapter, so many people join, and then from the next class onwards, no one joins. So if you are actually serious about the chapter, make sure you keep coming back for the subsequent classes as well. We've tried to cover the entirety of thermodynamics in 14 or 15 classes. It's a long chapter, and a tiny couple of things that are remaining: the Born-Haber cycle, the Kirchhoff's equation. We will cover that in this chapter and the ionic equilibrium chapter very, very soon. Once again, to all of you who are new to my channel, welcome. I am Pahul. I'm an alumnus of IIT Bombay. Yeah, and let me tell you all that I teach in English. If you want to learn in Hindi, then we have other channels of Vedantu. Yes, there is Vedantu JEE and there is Vedantu NEET. Over there you will get classes in Hindi from teachers like Love sir, Harsh sir and Arvind Arora sir. I'm pretty sure you know Arvind Arora sir. ठीक है? तो चलो जी, what we will do today is we will understand the basics of the chemical equilibrium chapter. And if you understand chemical equilibrium chapter, it's a very small chapter. We will try to cover it in just 3 classes. We will try to cover it in 3 classes. It's a very small chapter. But the thing is, if you do not understand this chapter, the chapter of ionic equilibrium will become difficult for you. ये चैप्टर अच्छे से नहीं किया तो आयनिक इक्विलिब्रियम एकदम मौत आ जाएगी फिर करते हुए, ठीक है? सो माय क्वेश्चन टू यू गाइज राइट नाउ इज, डू यू वांट टू स्टडी ऑन अ व्हाइट बैकग्राउंड और अ ब्लैक बैकग्राउंड? बिकॉज I will write and teach today. Everything I will write and draw in front of you and I will teach you. So tell me, do you want it on a white background or on a black background? You tell me. As I see over here, मैं देख लूँगा. Splendid, yes man, 9 PM is the estimated time of completion of this class, so don't worry. Pratik, yes, J 2021 aspirants can also see the session. It will be a revision session for you then. Okay, some people are saying white, most people are saying black. अच्छा, black वाले ज़्यादा हैं. Okay, I can see a number of people saying white as well, but black वाले ज़्यादा हैं. Let me turn this into a black slide. ठीक है, एक सेकंड में सबको एक ही बार में चूज करके. Yeah, just a minute. एक बार रुक जाओ यार. चलो, let's turn the background to black. Here we go. Fine. Something different. A little reflection can be seen. Yeah, you can see my camera setup and all. You can see the reflection of my laptop as well. तो चलो ठीक है, black पे कर लेंगे आज. Okay. I know Siddharth. You can see the background of my house in this black slide, but if that's what everyone wants, it's fine. Yeah. चलो जी, तो आते हैं. Let's come towards what we mean by a chemical equilibrium. Okay, very interesting chapter. New things we will learn today in just like half an hour. You'll learn so many new things. Chemical equilibrium. And we'll do it at a fast pace because now we have done a lot of chemistry. So this chapter I'll do a little faster, yeah, to save our times. So what is chemical equilibrium? See, chemical equilibrium is possible in reactions that can go in either direction. Okay, so chemical equilibrium can be established in reversible reactions. Now this definition of reversible over here is the real world definition of reversible. It is not the thermodynamics reversible process. Okay, when I say reversible reaction, if I say thermodynamically reversible, then it means a quasi-static process, infinitesimally slow process, etc., etc. But over here, whenever I say reversible reaction, it just means that the reaction can go forward and can come backward as well. For example, have you studied about the reaction of preparation of esters? Have you studied about the reaction of preparation of esters? Vedantu Pro is for all 3 subjects, my friend. Someone is asking about that. Yeah. So can you tell me a reaction of esters padha hai? So what do we do in reaction of esters? What we do is we take an acid, we take an alcohol, put it in water, they combine together to form the ester. Now, what you can do, you can take the ester, put a lot of water in it, the ester will break apart, give you alcohol and acid back again. So practically speaking, that's a reversible reaction because products can form, reactants can form products and products can form your reactants back again. ठीक है. So basic, simple, desi, घटिया idea of reversibility, not the thermodynamics idea, simple idea. Chemical equilibrium is possible in, या मैं green pen ले लेता हूँ, in reversible reactions. In reversible reactions. All right. Fine. Reactions that can go forward and backward at the same time. So again, as an example, I gave you for the reaction of esters. So I'll just write that reaction over here. Yeah. For example, you have a very simple acid. Yeah, this is the structure of acetic acid, CH3COOH. I have just drawn a more elaborate structure of this particular acid. Don't get scared by looking at it. You will learn the structures better in organic chemistry. And let's react it with some alcohol. Let's react it with methanol. Okay. So what's going to happen is, if this reaction goes forward, मैं नीचे बना रहा हूँ instead of making it over there. If this reaction goes forward, what you will get is C double bond O, CH3, yeah, and you will get your OCH3 on the right hand side. Yeah, this is your ester. Okay. So what you are basically doing is you are also getting a water molecule over here. And as I told you, if you take an ester and put a lot of water in it, it can go back as well. So I can have both sides of arrows possible. Instead of making two arrows, what I will make over here is an equilibrium arrow. Equilibrium arrow कैसे बनाएंगे? I will make the equilibrium arrow like this. Yeah. Right now it is from top to bottom, so that's why I've drawn it like this. If you have a reaction, something like A plus B in equilibrium with C plus D, I will draw it like this, which means that A plus B is going to C plus D is coming back to A plus B, so on and so forth. This is how you represent a chemical equilibrium. समझ गया how to represent a chemical equilibrium? If you need more time, pause, otherwise I'll move forward. चलो. अब दोस्तों, the next thing that I'll tell you will confuse you, but then I will explain it and you'll be like, okay. These chemical equilibria, okay, singular equilibrium, plural equilibria. You understand this, right? Latin singular plural. Yeah. So these different chemical equilibria are actually dynamic equilibria. A chemical equilibrium is a dynamic equilibrium. Now you must be wondering, sir, what on earth is a dynamic equilibrium? ऐ क्यों हुंदा सर? हैं जी? ये dynamic equilibrium क्यों हुंदा? Whenever I say the word equilibrium, let me ask you, if I say equilibrium, what comes to your mind? आपके दिमाग में क्या आता है जब मैं बोलता हूँ equilibrium? जरा बताओगे मेरे को? Can you tell me? It'll take me 10-15 seconds to read your chats because there's a slight delay in YouTube live. But as soon as I get your chats, I'll tell you. What do you guys think about equilibrium? तो बताओ. Ankit is saying chemical equilibrium, a condition in the course of a reversible chemical reaction which is known as change amount. हाँ ठीक है भाई. You did a very good copy paste. Yeah, equilibrium बोलो तो दिमाग में क्या आता है? Okay, so people have started giving the ideas. Kuldeep says balance. Siddharth says stable state. Okay. Someone is asking, is anti-abhyas a good mock test medium? For building speed, yes. Prodigious, thank you so much. So Anshuman is also saying stable state equal homeostasis, sorry. Okay. Nandini is saying stable, stability. I don't know anything about this. Okay, no problem, Omanshu. So we should all learn from Omanshu, because the thing is, a lot of times we are, reluctant to accept that we don't know something. हम बहुत बारी सकुचा जाते हैं. संकोच करना समझते हो हिंदी में? Reluctance in English. Yeah, कि कोई हमें पूछता है कि भाई तुम्हें ये आता है, तो we're like instead of saying no, I don't know this. Always accept if you don't know something, because once you accept you don't know something, you will start looking for a reason for it. Yeah. So Yogini is saying no heat exchange. Okay, Diksha is saying a balance, etc., etc. So a lot of people think about a balance or equality, and whenever I say equilibrium, 2-3 situations come into my mind. One situation could be where you have a क्या कहते हैं, तराजू कहते हैं उसको. I don't know how to draw it. तराजू कैसे बनाते हैं भैया? Does this make sense? Yeah, this is like your if you hold it and then the weights will equilibrate. I hope you understand. Or better still, I can make a seesaw kind of a situation. Yeah, something like this works. Yeah. यहाँ पे बड़ा डब्बा, यहाँ पे छोटा डब्बा. This is a balance. So when it balances, it's an equilibrium. Or what you can think of is, you know, this type of a situation. So you have a bowl. आपके पास एक कटोरा है, and in that कटोरा, in that bowl, you have a ball. Yeah, and the ball, you know, when you leave it, it'll move around, and at the end, it'll settle down at the bottom. Now, my dear friends, the thing is that is this moving when it is at equilibrium? No. Is this moving when it's at equilibrium? No. These cases are stable equilibria. ठीक है जी? These cases give you an example of a stable equilibrium. This ball just settles down over there, it's not moving. This guy settles down, it's not moving. It's not the example of a dynamic equilibrium. Let me give you a very beautiful example which everyone will understand. Yeah, and if you enjoy that example, I'll be a shameless YouTuber over here. If you enjoy that example, please hit that like button. What's the example? Let us take a bucket. Yeah, my bucket is green in color. My bucket is not very beautiful. It's a very cheap bucket. What I will do is I will take a very nice tap of water. Yeah, very simplistic, very minimalistic tap of water, and we are filling water in this particular bucket. ठीक है जी? So water gets filled. ये जो भी है. Cool. And then what happens is someone comes and they're like, you can't fill water. Why? Because I'm envious of water. Just giving a random example. Yeah, someone will come and he's like, तेरी बाल्टी में पानी नहीं चाहिए मेरे को, क्योंकि मेरी बाल्टी में पानी नहीं है. So there are people who are envious, and one such person comes and what he does is he takes this eraser and pokes a hole into your bucket. A very sad situation, but yeah. Right now you don't have M-seal, so you can't seal it. So what you have is a situation where water is coming in and at the same time water is flowing out. Right? Cool. So depending on the speed of water that comes in and depending on the speed of water that goes out, you will have a certain level of water. इस पे डिपेंड करता है आने की स्पीड कितनी है पानी की, जाने की स्पीड कितनी है पानी की, और कितना पानी यहाँ पे रह जाएगा, है ना? So what you observe and what your enemy observes is that the level of water does not change. Interesting, right? What you notice is that water is coming into the vessel, water is going out of the vessel, and ultimately the level of water does not change inside this box. What could be the reason? What could be the reason? Yeah. Armanur, I'm glad, man. Thank you. Suhas is saying, भाई संडे को क्लास नहीं होती यहाँ पे. Suhas, don't worry. We have classes 3 times a week for every, 11th class and 12th class. दोनों का 3 बार होता है हफ्ते में. Since it's a chemistry channel, bro. Will you be studying chemistry 6 days a week? Definitely not. Yeah. So BS Loga Satish is saying amount of water coming in is equal to amount of water going out. Okay, very good definition, but you can say something better. Yeah, Shakir is saying that same speed of water coming in and coming out. Pretty good. Speed makes more sense. Yeah, same amount bolenge, so we have to define a unit of time as well. That if in 1 hour 20 liters of water is coming in and the same 1 hour 20 liters of water is going out. So I think speed is a better way to talk about it. Yeah. That the speed of water coming in is equal to the speed of water going out. Instead of saying speed, yeah, speed sounds like a word that I would use if I'm a motorcycle rider, which I am. Let's try to use a word that chemists would use. Let's try to use a word that a scientist would use. Let's use the word rate. Rate of water coming in is equal to the rate of water going out. Do you agree? Rate in is equal to rate out, isn't it? Yeah. So because the rate of water coming in is equal to the rate of water going out, the level of water overall remains constant. Yeah, because of that fact that we've written over here, because of this, I can write over here that the overall level, okay, overall level remains constant. I am pretty sure everyone agrees with this. Yeah. Now my question to you is, let's say there is a water molecule called Harry. Yeah. There's a water molecule. He is my favorite molecule. Let's call him Harry. Yeah. And let's say another water molecule, because this is Harry, we'll call her Hermione. So we've got Harry and Hermione over here. Do you think Harry and Hermione will stay inside this bucket for the longest period of time? Yeah. If I'm observing this bucket of water for, let's say, 2 hours, water is coming in constantly, water is going out constantly, will Harry and Hermione stay inside this bucket? Yeah. Abdur is asking, why is he your favorite water molecule? Just because his name is Harry. Obviously not. Yeah, because in 1 hour, some more water would have come in. Harry and Hermione would have gone out already. Now do you understand why I call it a dynamic equilibrium? अब आपको समझ आया कि ये dynamic equilibrium क्यों कहा जाता है? There is motion. Water is coming in, water is going out, but overall the level remains constant. ठीक है जी? Overall पानी का level जो है वो constant है. That's why I call it a dynamic equilibrium. Yes. Dynamic because there is some motion going on. It's not a stationary system. It's not a, standing in one place system. It is moving around. But overall, this motion gives you a constant level of water. So that is why we call it a dynamic equilibrium. Now, what does this have to do with chemicals? Let me tell you something. I'm going to erase this. If you need more time, you can pause this instance right now. Otherwise, here we go. अब आती है बात chemistry की. Yeah, let's talk about chemistry now. So in chemistry, let's take a very generic reaction. A plus BB. These are the stoichiometric coefficients. These are the reactants. They are going to the products. C times C plus D times D. I am sure you have seen this reaction earlier as well. Somewhere or the other, you've seen this type of a reaction. Yeah, stoichiometric coefficient, reactant, stoichiometric coefficient, reactant, stoichiometric coefficient product, stoichiometric coefficient, and the product. Reaction is happening both sides. Yeah, reaction is happening in both sides. Reactants are combining together to make products. Products are combining together to make reactants. I live next to a highway, so the truck is always excited. Some or the other truck is always excited. Anyway, so ये बात है यहाँ पे. Now I'll write a statement and then you'll understand why we call it a dynamic equilibrium. Okay. At chemical equilibrium, please make sure you write this statement down. At chemical equilibrium, okay, rate of the forward reaction rate of the forward reaction is equal to the rate of the backward reaction. Nice, right? It's not like A and B were reacting, they stopped reacting. No, these guys are still reacting with each other. They are creating some molecules of C and D. And then some molecules of C and D are also reacting. They are again creating A and B. This interchange is always going on. Yeah, get the idea? ये reaction यहाँ से आगे भी जा रहा है, यहाँ से पीछे भी आ रहा है. So at a chemical equilibrium, the rate of the forward reaction is going to be equal to the rate of the backward reaction. Exactly like the case with water. That's why a chemical equilibrium is always a dynamic equilibrium. Did you understand what we mean by dynamic equilibrium? Yeah? आगे समझ? I'm pretty sure this is a good example that I've taken to explain you the concept of dynamic equilibrium. समझ आ गया तो बता देना. Someone is astonished looking at the black screen. Yeah, since I had to write today and I don't have any prepared slides, I thought I'd do it on a black slide. ठीक है दोस्तों. Ankit, we'll talk about the concentrations as well. So the other example of static equilibrium chemistry doesn't really happen, brother. Static equilibrium hota nahi hai. You can think about it like this. When you burn paper, when it's entirely burnt, it's static equilibrium. Yeah. Got it? Okay. So A and B are reacting together to go to the C and D, that we call the forward reaction. C and D are reacting together to form A and B, that is something that we call as the backward reaction. The forward reaction has the same rate as the backward reaction. So overall, the concentrations of A, B, C and D do not change at a chemical equilibrium. This is the next thing that we will write. At chemical equilibrium, okay, at chemical equilibrium, how do we define the chemical equilibrium? Like what do we observe at chemical equilibrium? Concentrations, okay, concentrations of reactants and products are not changing anymore. That's what happens at chemical equilibrium, that the concentrations of the reactants and products become a constant value. As simple as that. Yeah, बस यही करना है. Concentration equal हो जाएगी. I mean not equal. Concentration will not change. ठीक है. तो थोड़ा सोच के देखते हैं यार. How would it look like practically? ठीक है. इसको practically सोच के देखते हैं. I'm gonna erase a lot of things over here now. You can rewind and pause the video anywhere you want. तो अब let us think about a chemical reaction. Okay, let's think about a chemical reaction. Let us think about what do we think about? मैं सोच रहा हूँ कि ऐसा कौन सा रिएक्शन लिया जाए which you can see is, you know, a dynamic equilibrium. It's very hard to find a practical example of dynamic equilibrium in chemistry. चलो random example ले लेते हैं. Okay, just imagine this happens. This doesn't really happen in reality. The thing is a little different. But let me just give you this ghatiya example. Okay, so what we can imagine right now is that iron plus water. Okay, just for imagination I'm doing this. Iron plus water gives you rust. And assume that rust, this is a special kind of rust that, you know, can reverse itself and form iron and water back again. ठीक है, iron plus oxygen बोलना चाहिए मेरे को, in the presence of water. That's a better way to talk about it. Yeah. So iron plus oxygen will give you rust, which is the oxide of iron. It happens in the presence of water. So ठीक है, ऐसे मैं लिख सकता हूँ. Yeah, and this is a special kind of rust which is, you know, getting back into iron and O2 again. Now people, let's think about it. If I take 1 kilogram of iron and oxygen already is in excess, yeah, does it mean that at equilibrium, okay, this is something that is common sense. I am trying to ask you a question to make it even more clear. Yeah. Tell me, using your common sense, that at equilibrium, is it necessary for iron to be 0.5 kilogram and rust to be 0.5 kilogram? Or if we have taken, let's say, 1 mole over here, is it necessary for me at the equilibrium that this is half a mole and this is also half a mole? क्या ये जरूरी है? Is it necessary for my reactant and product to have the same concentration, to have the same mass? Is it necessary? Tell me, what do you think? सिद्धार्थ, आई वॉज थिंकिंग अबाउट सैचुरेशन ऑफ अ सॉल्ट, बट आई थॉट यार ये देसी एग्जाम्पल लेते हैं थोड़ा. क्या सोच रहे हो? Some people are saying yes, like Aryan says yes, and Uma, I know man. So the thing is that when I use a black screen, this happens. Yeah, ये थोड़ा ऐसा weird सा आ जाता है black screen में. I just want to tell you all that if we teach on the black screen, it'll look like this because the screen is not perfectly matte finished. There is a certain amount of reflection, so it will reflect whatever is in front of me. Yeah, so most people are saying that it's not necessary. Absolutely correct, it's not necessary. Equilibrium can be attained at any concentration. It depends entirely on the mood of the reaction. वो हर रिएक्शन पे डिपेंड करता है उसका क्या मूड है, उसने इक्विलिब्रियम अभी करना है, बाद में करना है, क्या करना है. सो इट इज पॉसिबल, ओके, इट इज पॉसिबल दैट आई टेक 20 moles of iron initially. Finally, what I find is, what do we mean by finally? Finally, we have reached the equilibrium. Equilibrium पे जाके रुक जाना है. At equilibrium, we will be okay, fine, cool. So at equilibrium, I notice that iron has reduced to 18 moles. Yeah, and you are, let's say, getting 1 mole of rust. Assuming that it's Fe2O3. थोड़ा मस्त एकदम कॉम्बिनेशन वाला डाल दिया अपन ने. सॉरी, Fe3O4 होगा, Fe2O मान लो चलो इसको. शुड वी कंसिडर इट एज FeO? बिल्कुल सिंपल वाला लेते हैं चलो. सो लेट्स थिंक अबाउट 2 moles ऑफ दिस. थिंक अबाउट द सिंपलेस्ट ऑक्साइड पॉसिबल ओवर हियर. Fe3O4 नहीं लेते, Fe2O3 भी नहीं लेते. Let's just think about the simplest oxide. You can think about Fe2O3 as well. Then 1 mole हो जाएगा. A very specific example that I'm taking over here. This is all imaginary, by the way. Not a great example for an equilibrium, but again, since we can think about it, I've taken this example. Yeah. If I start taking example of ammonia and N2 plus H2 giving NH3. It's not very easy to imagine. This is something we can imagine. We know what an iron block looks like. We know what rust looks like. So let's just take the simplest type of rust. ठीक है? So यहाँ से मान लो 18 moles of iron were there initially. 2 moles of iron have turned into rust, and then equilibrium gets established. Then this is the final concentration. At equilibrium, you can have more reactant, less product. It is possible, depending on the mood of the reaction, depending on the temperature, depending on the conditions of moisture, etc., etc., it is possible that this guy reduces to 2 mole and gives you 18 mole of very simple rust. Okay? That is also possible. So, these concentrations depend on the mood of the reaction. The mood of the reaction changes basically with temperature. Now, if I am a scientist in a research paper, can I write, I noticed a reaction. The reaction's mood was such that it formed more product than the reactant. मैं एक वैज्ञानिक हूँ और मैंने एक रासायनिक क्या कहते हैं इसको? What do we call a reaction in Hindi? मैंने एक रासायनिक प्रतिक्रिया की. उसके पश्चात मुझे ये भाप हुआ कि रिएक्शन का मूड ऐसा था कि उसको प्रोडक्ट बनाने में ज़्यादा मज़ा आया, रिएक्टेंट सारे खा गया. वो मज़ा नहीं आएगा ना ऐसे. It won't look good in a research paper. So we need to put some mathematics. Instead of saying mood of the reaction, we need to put some mathematics in place. Yeah? Instead of saying mood of the reaction, कुछ मज़ेदार बोलते ना यार. Let's talk about the mathematics in a better manner. I can say that I found as a scientist that when I did this reaction, the rate was achieved, equilibrium was achieved when the rate of the forward reaction was equal to the backward reaction, and that happened to be when the products were more than the reactants, although all the reactants weren't over. Get the concept here? We need some mathematics to be involved. So my dear friends, for mathematics to be involved, what we will write over here is a very interesting thing which you will see once again in chemical kinetics, which is in 12th class. We will learn about the law of mass action. This particular law, my dear friends, is an empirical law. Empirical law. What do we mean by an empirical law? Empirical means experimental. For all of you who have a misconception about the meaning of the word empirical, empirical literally means experimental. So what scientists did, it's somewhere in the 1800s as far as I remember. Yeah, what they did was they just started doing reactions and then they tried to see the speed of the reaction, and then they tried to see whether it is proportional to the concentrations of the reactants or not. Okay, so law of mass action. Okay, so what does law of mass action say? Let me tell you. For elementary reactions, which means single step reactions. What are single step reactions? I'll give you an example, but you will understand this even more when you start learning organic chemistry. So for an elementary reaction, the rate can be written like this. चलो एक reaction लिखते हैं यहाँ पे. Let us say we have a reaction where A times A plus B times B is going to products. Fine. It is an elementary reaction, single step reaction. What's happening is A and B are combining together to give you the product directly. It's not like A and B combine you to give C and D, then C and D combine to give E and F, then E and F combine to give X and Y. Multiple steps are not involved in this particular reaction. It is a single step reaction. एक ही बार में हो रहा है. Fine. How to know whether a reaction is single step or not? You have to do it in the laboratory. When you do it in the laboratory, you'll realize whether it's a single step reaction or not. In this chapter, they will ask you only elementary, that is single step reactions. So no need to worry about it. Okay? So assume this is a single step reaction. It's also called an elementary reaction. I'm pretty sure you've studied that in 9th, 10th class as well. So for such kind of reactions, the rate of this reaction can be written proportional to concentration of one of the reactants raised to the power the stoichiometric coefficient of that particular reactant into concentration of the second reactant raised to the power of the stoichiometric coefficient of that reactant. पहले ये लिख लो, then I'll try to explain to you why this is happening. First write it down, then I will tell you why this is happening. Okay, I'll give you some examples as well, don't worry. ये एक बार लिख के देखो. अंकित कुमार सिंह मेरे दोस्त, पहले रामायण पूरी पढ़ लेते हैं, फिर पूछना भी रावण की रावण की बेली में ही क्यों मारना था तीर, है ना, रावण के सिर पे क्यों नहीं मार दिया. पहले रामायण पढ़ लेते हैं पूरी, फिर पूछ लेना भैया. Gagan, basically at equilibrium the concentrations are not changing. See, some of reactants and products concentrations it's not necessary, because the stoichiometric coefficients can be different. Yeah, 1 mole of a reactant can give you 20 moles of product as well. So the sum doesn't work all the time. I hope you understand that. Siddharth, I will turn it to white in the next class. Now that we are doing it on a black screen, let's commit to it for the entire class. Kaustav, don't worry man, एक बार देख तो सही मैंने लिखा क्या है, सब समझ आ जाएगा. Okay, तो ये बात आती है, rate is proportional to a to the power a into b to the power b for an elementary reaction. Let's now look at it with a proper example. एक example लेके देखते हैं. Let us assume that this reaction N2 plus H2 giving you NH3 is an elementary reaction. Let us assume. Okay. So my dear friends, what I can write after balancing the equation is something like this. This is how the equation is balanced. So can I write rate of this reaction is going to be proportional to, according to the law of mass action, it's going to be proportional to the concentration of hydrogen raised to the power 3 into the concentration of nitrogen raised to the power 1. What do we mean by concentration? See, concentration can be taken in moles per liter. Moles per liter of solution. What is this? Basically molarity. है ना जी? तो concentration is always taken in molarity. Okay? ये जो ब्रैकेट में लिखते हैं, ब्रैकेट में कुछ भी अगर लिखूंगा मैं, this means the molarity of that particular substance. Concentration समझते हो? Do you understand the meaning of the word concentration? We have discussed that in mole concept class. Yeah? So whenever I write something in brackets, it means that I'm talking about the concentration of that specific thing. So assume that, this entire reaction is happening inside a solvent. Amount of H2 dissolved in the solvent, you will get the molarity of H2, you will get the molarity of N2 in the same manner. So the rate of this reaction will be proportional to H2 raised to the power 3, N2 raised to the power 1. So if I have to remove the proportionality constant, what do I have to do? If I have to, Avril is asking, can molality be used? It can be used, bro. Not a problem. Yeah, it can be used. It's just that you will have to take everything in molality. But technically we use molarity so that everyone uses molarity. And it's just a convention to use molarity over here. So rate can be written as K times something something. Yeah. ठीक है, ये लिख सकता हूं मैं. Now what about this K? This K is basically known as the rate constant of the reaction. How do you determine the rate constant? This rate constant is determined, okay, this rate constant is determined experimentally. Okay, it is different for every reaction. ठीक है, इसको एक्सपेरिमेंटली डिटर्मिन करेंगे, ये हर रिएक्शन का अलग अलग रहेगा. एंड इट ऑल्सो डिपेंड्स ऑन टेम्परेचर. दिस इज द रिएक्शन. Rate will be equal to some constant times H2's concentration raised to the power 3, N2's concentration raised to the power 1. This is known as rate constant. It can be determined experimentally, different for every reaction, depends on the temperature. Naveen, yes, next 2-3 classes will be of this chapter only. ठीक है जी, चलो बढ़िया है. Siddharth, so the thing is, whenever we talk about chemical kinetics, we are focusing only on one side of the reaction. When we talk about equilibrium, we are considering one side and the other side as well. So why do we segregate these two chapters? Because it's easy to study equilibrium separately, it's easy to study kinetics separately, but in reality both the things are happening at the same time. So I hope you understand you should not mix these two concepts together in one place. Yeah, ठीक है, चलो ये हो गया. Now my dear friends, once we've written all this, let us jump back to an equilibrium reaction. Yeah, एक equilibrium reaction पे जाते हैं. Once again, let's take the most basic idea. A times A plus B times B goes to C times C plus D times D. अब मैं ना कुछ अजीब चीजें लिखूंगा. I'll write things in a very interesting manner. Rate of forward reaction. Rate of forward reaction. What is forward reaction? A and B combining to go to C and D. How can I write the rate of forward reaction? Rate of forward reaction can be written as K times concentration of A to the power A into concentration of B to the power B. Let's call this K forward. This is the rate constant for the forward reaction. If I have to determine this value, I have to do an experiment to see how fast this reaction goes forward. Okay. This is molarity of A, this is molarity of B, this is stoichiometric coefficient of A, stoichiometric coefficient of B. Fine. Similarly, can I write rate of backward reaction? Can be written as K backward, K backward into C to the power C into D to the power D. क्या मैं लिख सकता हूं? Rate of the forward reaction is A to the power A, B to the power B into constant. Rate of backward reaction is C to the power C into D to the power D into a constant. This constant is not equal to this constant. Yeah, this is a different reaction. This is a different reaction. Let's consider the forward reaction and the backward reaction separately. Let's think about them as separate entities. उनको अलग अलग entity मान के सोचेंगे. So rate of forward reaction can be written like this because of the law of mass action. Rate of backward reaction can be written like this because of law of mass action. चलो ये हो गया. Now my dear friends, once we have written this, can I write, okay, I'll use this part of the screen now. Can I write that at equilibrium, okay, assume that equilibrium is achieved. अब अपन equilibrium पे आ चुके हैं. We're like, okay, fine. AB combined to go CD, CD combined to go AB. Now we have reached a point where A and B's speed is equal to C and D's speed. So both of them, you know, both sides are at equilibrium now. Dynamic equilibrium, but equilibrium. Their concentrations are not changing anymore. Concentration of A has become fixed, B has become fixed, C has become fixed, D has become fixed. They need not be equal. It's not necessary for their concentrations to be equal. It is possible that this is 10 moles, this is 10 moles, this is 1 mole, this is 0.5 mole. Possible hai. Okay? At that point also, the reaction can stop, you know, moving in either direction overall. So equilibrium kahin bhi achieve ho sakta hai. Once the equilibrium is achieved, can I say that the rate of forward reaction is equal to rate of backward reaction? That is how we defined equilibrium. So because of that, can I write, okay, यहाँ पे मैं लिखने की कोशिश करता हूँ. I don't have enough space, but still I will try to use my calligraphy skills to fit it in this small space. Can I say Kf into A to the power A into B to the power B is equal to Kb into C to the power C into D to the power D? ये लिख सकता हूं. Very obvious, right? Rate of forward reaction is equal to rate of backward reaction at equilibrium. Fine, clear. Now we will rearrange. What we will do is rearrange. Let us rearrange. How will we rearrange? We will write. Where is my blue pen? K forward divided by K backward. Can we write this? This would be equal to, this would be equal to C to the power C into D to the power D divided by A to the power A into B to the power B. Can you see that? K forward by K backward is equal to CC DD by AA BB. ये तो बहुत simple हो गया. This has become very simple now. We have some mathematical idea over here. Yes, my dear friends, let me tell you, okay, let me tell you in this particular space on the board, because I don't have a lot of space. I do have a lot of space. I am not very good at managing the space. Yeah, so ये सब आ गया. My dear friends, I will define something called K equilibrium. This K equilibrium is basically equal to the rate constant of the forward reaction divided by the rate constant of the backward reaction, which is equal to, in this particular case, C to the power C, D to the power D divided by A to the power A into B to the power B. I haven't written brackets over here just for simplicity. मैंने यहाँ bracket नहीं बनाया ताकि जल्दी लिख दूं. ठीक है? So K equilibrium is equal to the concentration of C raised to the power stoichiometric coefficient, concentration of D raised to the power stoichiometric coefficient divided by concentration of reactants raised to power their respective stoichiometric coefficients. This particular form is valid at equilibrium. Yeah, सो व्हाट्स द सिग्निफिकेंस ऑफ दिस? इसका अभिप्राय क्या है, इसका मतलब क्या है? देखो, इफ माई रिएक्शन at equilibrium has more products, less reactants, K equilibrium will be a bigger value. I'll repeat my statement. At equilibrium, if my reaction has more products, less reactants, my K equilibrium will be a bigger value. If K equilibrium is bigger, I can say that my reaction has the mood of going towards the products. Yeah. And if the reaction at equilibrium has more reactants, less products. Yeah. Let's say the reaction is as such, its mood is not to react. It just makes a little bit of product and like, okay, mera kaam ho gaya, bye. I don't want to do anything more. Yeah. Understand? The reaction has more reactants at equilibrium than products. So K equilibrium will be a smaller value. At equilibrium in the laboratory, I can easily measure concentrations, right? Moles per liter निकालना कितना ही मुश्किल है. How difficult is it to calculate moles per liter? Not very difficult. If I know the stoichiometry, I can calculate moles per liter of everything very easily. We'll see that in questions. But do you understand that if K equilibrium is higher, the reaction likes to move towards the products and settle down? If the K equilibrium is a small value, the reaction likes to be towards the reactants, doesn't react much, and then becomes equilibrium. ठीक है, बात बनती है थोड़ी. So let me refresh my YouTube. I don't know why YouTube has logged me out of my own account. Can't read any chats. Okay. लोड हो जा मेरे भाई. हो गया. ठीक है, ये हो गया. Someone is asking, why do we write it in square brackets? Sukman Preet is asking, why do we write in square brackets? Just a notation, bro. We write it in square brackets to show that this is concentration. ठीक है? Okay, people. So, what have we learned till now? Let's summarize and then look at a question. अभी question देखोगे तो ज़्यादा मजा आएगा. What have we learned till now? We have learned that in chemistry, some reactions are reversible. That products can react to form reactants and reactants can form products. Both sides of the reaction can happen. And in reality, most reactions are reversible in nature. Not every reaction will go 100% to the products. Not every reaction will go 100% to the reactants. It will become an equilibrium somewhere in the middle. That equilibrium is a dynamic equilibrium. When the speed of your forward reaction becomes equal to the speed of your backward reaction, we attain an equilibrium. And at equilibrium, the concentrations of the reactants don't change. The concentrations of the products don't change. They need not be equal. Concentration of the products can be different. Concentration of each reactant can be different. But when we notice their concentrations at equilibrium, they do not change. Yeah? Which means that if one reactant is at 1 mole, it will stay at 1 mole if the reaction is at equilibrium. Okay, concentration is generally taken in moles per liter, molarity. Then we learnt about the law of mass action, which says that experimentally we determined that the rate or the speed of a reaction depends on the concentrations of the reactants. है ना? ठीक है? Now you must be wondering, sir, why powers of, why powers are taken? देखो, just to give you a simple example. This N2 plus 3 times H2. Yeah. Can I write this like N2 plus H2 plus H2 plus H2? Yeah. Now, how does a reaction happen? How does a reaction happen? Reactions basically happen when N2 has high energy, H2 has high energy, H2 has high energy, H2 has high energy. All of these combine together and collide. है ना? When this guy collides with 3 hydrogen molecules at a certain amount of speed, at a certain orientation, what will get formed is ammonia. यही हो रहा है ना? This guy is colliding with this guy, is colliding with this guy, colliding with this guy. Collision should be of a good speed and then this reaction will happen. That's how reactions happen. Okay. Now, can I say that the rate of the reaction, the speed of the reaction depends on how much N2 is there, how much H2 is there, how much H2 is there, how much H2 is there? So I can very simply say from here that the rate will be proportional to how much N2 is there Can I say just 2 mole? No. If there is 2 mole of N2 in this entire room that I am in, it's a very small amount of N2. That's why we take a concentration moles per liter. It's like taking the density. है ना कि इतनी स्पेस में कितना है भाई वो बता, पूरे रूम में जितना मर्जी हो. I care only about the container. Yeah. So that's why we take moles per liter. So concentration of N2 into concentration of H2 into concentration of H2 into concentration of H2. Rate इसी पे depend करेगा. Very logical idea. You can verify this experimentally as well. So that's why we say raised to the power 1 H2 raised to the power 3. Get it? Why stoichiometric coefficients? So we learnt about the law of mass action, which is quite obvious when you think about it, and we, instead of the equilibrium, instead of the proportional arrow, we can write a constant over here. This is known as the rate constant of the reaction. This tells you about how fast the reaction's mood is. How fast does the reaction want to happen? Cool. So we understood that this is the rate constant. It has to be determined experimentally. There's no other way to determine it. So what we did later, we said that at equilibrium forward reaction, we said at equilibrium forward reaction is equal to backward reaction rate. So we can equate the equations. Yeah, we can simply say that Kf into the reactants is equal to K backward into the products. Therefore, we got the idea that K equilibrium is equal to forward rate by backward rate constant, which is equal to product divided by reactant. As simple as that. This is what we have learned. And my dear friends, this particular K equilibrium is a constant value for a specific reaction at a constant temperature. ठीक है जी. This K equilibrium is a constant value for one particular reaction at constant temperature. Only if you change the temperature, the K equilibrium of a reaction changes. Fine. So now let's try to look at some एक ऐसा example कर लेते हैं. Then we'll go to the question. Okay. So can you once again, taking this example, can you write the K equilibrium for this reaction? Can you try to write the K equilibrium for this reaction? K equilibrium can be written as products, concentration of products, NH3 का square divided by concentration of the reactants, N2 raised to the power 1 into H2 raised to the power 3. Got it? This is the K equilibrium for this reaction. Life is sorted. Now let us go towards a question. ठीक है? Before I go to a question, let me tell you, if you want to join Vedantu's Pro subscription, because I'm pretty sure now you are getting serious about it. Your preparation needs to be a lot more focused, lot more guided. So if you need regular classes from our master teachers at Vedantu, live classes will be there, interactive classes on Vedantu's patented platform. You will have lots of doubt solving as well. Very beautiful courses. All you need to do is go to the description box down below. There is a code, there is a link in the description box. You scroll down a little and there is a link called Vedantu Pro subscription something. Yeah, उसके साथ में ये लिखा होगा, yeah. Sorry. So PH Pro is written over there. Just open that link, choose your class, 11th class, 12th class, droppers, whatever course you want to choose. You can enroll for 1 month, 3 months, 6 months, 12 months as well if you want. Yeah. And PH Pro is the coupon code that will give you a 20% discount. So you can check it out. तो चलो ये reaction करते हैं. Okay. Let's do this reaction. Very nice, very simple reaction, and it will tell you about how to solve these questions. Okay. Let's do this, and then we will also try to take a variation of the same question, and I think I'll give you that as your homework. चलो ये करके देखते हैं. So what do we have? We have A plus B going to 2 times C plus D. Right? This is what we have. Now people, what has been given to us initially? Initially we have 1 mole of A and 1 mole of B in a 1 liter vessel. ठीक है. सो मैं इसको लिख दूंगा, इनिशियली you've got 1 mole and I'll write this entire thing is present in 1 liters. Okay, so we have a 1 liter vessel like this bottle, 1 liter. This is 0.8 liters by the way, but assume 1 liter. Yeah, so you have a bottle like this or a container like this, you place 1 mole of A in it, 1 mole of B in it initially. So what will happen? Reaction will start happening, some products will get formed, then the products will also start reacting, some reactants will get formed, mast ekdam inka mumbo jumbo hoga, and then finally they will reach equilibrium. Finally, A plus B, 2C plus D, both of these reactions will have the same speed, both of these reactions will have the same rate, and you will reach equilibrium. So at equilibrium, what has been given to us? At equilibrium, I am getting 0.4 moles of C. So that is the information that is given to us. At equilibrium, I have 0.4 moles of C. My dear friends, can I say something like this? 1 minus X ho jayega A. Same thing will happen with B. X moles of A reduce, X moles of B reduce. So if X moles of A are reducing, how many moles of C will be produced? 2X moles. है ना? Stoichiometry, do you understand? 1, 1, 2 and 1. Right? So if you are using 2 bread slices, you are getting 1 sandwich. So similarly over here, if you are using X amount of A, you are getting 2X amount of C. Because 1A is associated with 2 times of C. So 1X, yeah, X amount of A will be giving you 2X amount of C. है ना? Understood? X amount of A will give you 2X amount of C. Okay, fine. So what I can write over here is, yeah, from here I can see 2X is equal to 0.4. So I can say X is equal to 0.2. You don't need to write it. In your brain you can do it. I'm just making it a little more obvious, making it a little more simple for you to understand. So यहाँ से आ जाएगा X equal to 0.2. So my dear friends, I can say that A is 1 minus 0.2, that is 0.8. 1 minus 0.2, that is 0.8. That gives you 0.4 of C, and D कितना बनेगा फटाफट से बताओ. 1A gives you 1D. So 0.2 of A has given you how much D? 0.2 of D, yes. Very simple. So 0.2 moles of A have gone away, 0.2 moles of B have gone away, 0.4 moles of C have been created, and 0.2 moles of D have been created. Very simple idea. Yeah, basic stoichiometry. If you don't understand stoichiometry, then please revise the chapter of mole concept. Okay, chalo ye ho gaya. Fine. Cool. Now, my dear friends, how do we write the, yeah, and this is also in 1 liter by the way. How do we write the equilibrium constant now? Yeah, how do we write the equilibrium constant? यहाँ लिखते हैं. We have some space over here. Let's write it over here. K equilibrium will be equal to C square D to the power 1 upon B into A. Only C has a power of 2, rest of them have powers of 1. Yes. Now my dear friends, you have to remember that you have to take concentrations over here. Right now what we've written is moles. If I write concentrations, what will be that? Moles per liter, moles per liter, moles per liter, moles per liter. Thankfully, it's a 1 liter vessel. So dividing by liters doesn't change our calculation. ठीक है? Concentration लेनी है. You can start with moles, you can end with moles. After that, divide by volume to get the concentration. ठीक है? तो यहाँ पे K equilibrium कैसे लिखेंगे अपन? I'm gonna erase this jazz now. The reaction is already given in the question. Yeah. So K equilibrium is equal to concentration of C raised to the power 2 into concentration of D raised to the power 1 divided by concentration of A into concentration of B. Each of them raised to the power 1 because that's their stoichiometric coefficient. बस ये calculation है. Yeah? तो क्या आ जाएगा इसका आंसर? 4 into 2 into 0.4 divided by 8 into 8. Yeah, यही आ जाएगा. This is 0.4 by 8. ठीक है जी. 1 by 20, 0.05. So this is my K equilibrium. Can you tell me what's the unit of K equilibrium over here? Unit बता दो. Tell me what's the unit of K equilibrium over here? Moles per liter, moles per liter, moles per liter, moles per liter, moles per liter. Molarity cubed divided by molarity squared. K equilibrium is basically 1 by 20 or 0.05 mole per liter. Okay. Unit is important. And do you realize that K equilibrium's unit will be different for different reactions? Depends on the powers of the concentrations and of the products and the reactants. This will have moles per liter because C is squared, so moles per liter squared. Once again moles per liter, moles per liter, moles per liter. So 1 moles per liter will remain. ठीक है जी? Got it? तो ये आ गया आंसर. Now the homework question for you is same thing, but the vessel that you are taking is a 2 liter vessel. 1 liter vessel की जगह आप ले लो 2 liter vessel. Okay. So there is a 2 liter vessel now. 2.0 लिखा है वहां पे, it's not 20. So we have a 2 liter vessel. This is now your homework. What you have to do is, okay, answer in the comment section with proper units. And some people must be wondering, sir, you said K equilibrium, but it says Kc. Kc means K equilibrium for concentration. In the next class, we will learn that K equilibrium can be written for pressure as well. That is called Kp. This is K equilibrium for concentration. When you take the concentration, that is moles per liter of everything. So that's the homework question. Answer in the comments with proper units. 1 लीटर की जगह 2 लीटर का वैसल है अब. Okay, fine. Chalo ji. Ved is asking, sir, why do you drink so much water? Do you have a problem? Yes, I have a problem with. I am not a human. Actually, I'm an ocean. So you know, ocean is just water. So I'm just maintaining my oceanness by drinking this amount of water. I mean, if you're a human, you don't need to drink water because humans are not 70% water, aren't they? Yeah. Aviral, because reactants are reacting, so reactants will reduce, isn't it? भाई देखो ना, एक finally idea देता हूँ थोड़ा सा दोस्तों. Some people are getting confused with the calculation. Let me give you this idea, okay? 2 bread plus 1 cheese gives you 1 sandwich. If initially I am taking 30 bread slices and 15 cheese slices, and at equilibrium, what do you mean by equilibrium? Let's say you made some sandwiches and now you're tired, you don't want to make any more sandwiches. So at equilibrium, what you've done is you have made, let's say, 5 sandwiches. If I tell you you've made 5 sandwiches, how many breads are remaining? 30 minus 2 times 5. 5 is what? This guy. 2 is what? The stoichiometric coefficient of bread. कितना आ जाएगा ये? 20. How much cheese is remaining? 10. 5 sandwiches. So how do you calculate the equilibrium constant? 5 divided by 10 and 20 squared. चमकी बात. Just basic क्या कहते हैं? Stoichiometry. Okay. So similarly, if this was A plus B gives you 2C plus D, initially, if I have 1, 1, 0, 0, finally someone tells me at equilibrium that this is 0.4. How is this 0.4? I can basically write it as 1 minus x, 1 minus x, 2x and x. Can I? Obviously yes. Let's say x moles of A is used, x moles of B will be used because 1 is to 1. 2x moles of C will be produced because 1 is to 1 is to 2. X moles of D will be produced because 1 is to 1 is to 1. Okay, so it has been given to me that 2x is equal to 0.4. It implies x is equal to 0.2. Therefore, everything else. Got it? Harsh, yes, that's what I'm saying. The dimension is not fixed. It depends on every other reaction. I've already said that statement. Cool. People, so that's it for today's class. We have studied a lot about chemical equilibrium today. If you start reading a book, then half of the chapter is already done. Okay? So the next class of this chapter is going to be there on Thursday, and we will discuss about different questions, different ways to write chemical equilibrium. Yeah, right now we've done it in terms of concentrations. We'll do it in terms of pressure as well, because there are gaseous reactions. And then the last class will be devoted for Le Chatelier's principle. Our goal is to complete this in 3 classes, saving all of our times. Ibrahim is asking, is NCERT enough for this chapter? Much more than enough. Just read NCERT, you'll be good. Cool. So people, that's it from my side for today's class. Thank you so much for joining in. If you enjoyed the class, make sure you hit that thumbs up button, stay subscribed, share it with as many people as you can. Tell them to subscribe as well, because if you want good quality education online for chemistry in English for free, then I think Catalysis has a good monopoly over here. Yeah, so chalo, that's it. Thank you so much for joining. I'll see you next time. Until then, take care.